So hopefully the last example convinced you that when we have the composition of a function and its inverse, the output will just be equal to the input. But let's prove that in general now. So on the left-hand side here, I have f inverse after f of x. And remember from our example, f of x was 2x plus 5, and we worked out that the inverse then was x minus 5 divided by 2. So when I have f inverse x after f of x, essentially what I'm doing is subbing in f of x into f inverse. And f of x is just 2x plus 5. So that means wherever I see x in my formula for f inverse, I replace it with 2x plus 5. So I'm just subbing in 2x plus 5 for x here. And now I can simplify this expression. 2x plus 5 minus 5 over 2. The 5's cancel there, so I just get 2x over 2, which is just equal to x. So this composition then is just equal to x, which is our original input. Now moving on to the right-hand side then, this time I have f after f inverse. So this time I'm subbing in f inverse as an input into f. And f inverse is x minus 5 over 2. So that's what I'm going to sub in to f wherever I see x. Okay, so I can simplify this expression now. So when I multiply that bracket by 2, I'm just left with x minus 5 because the 2's cancel, and then plus 5 at the end, and then the minus 5 and the plus 5 cancel, leaving me with x again. So the composition in this particular order is also equal to our input x. I just need to point something out here before we continue. A function has an inverse if and only if it is bijective. If the function is not bijective, then the inverse does not exist. And if you are unsure of what I mean by a bijective function, there is a video tutorial dedicated to that, so maybe check that out. Just note the phrasing I'm using here. If and only if is a special type of phrase that you may come across, and it means that the statement works both ways. So not only can I say that a function will have an inverse if it is bijective, I can also say that if a function is bijective, that implies that the inverse does exist.